Yeah, guys, we'll be starting the session now. Can you hear me? Can someone confirm? One of you? Okay, fine. Okay, so we'll be starting with this first question. It is from machines, transformers, and it is from GATE 2019 instrumentation. Uh, although these sessions are for electrical, we'll be taking inspiration from other papers where similar questions have come. So this is from instrumentation, GATE 2019, technical question 4. So in figure A and B as shown below, the transformers are identical and ideal, except that in the transformer in figure B is center tapped, where center tapped is connected to ground. So assuming ideal diode, the ratio of root mean square voltages across resistor R in figure A to that of figure B is. So these four options are given: root 2 is to 1, 2 is to 1, 2 root 2 is to 1, or 4 is to 1. So it's a fairly easy question. Although it is looking like a transformer and it may come under machines question, but it is a basic networks question from a simplicity point of view. So let us see directly into the figure B, where if V naught sine omega t is given, and when we see it from a positive cycle point of view, on the top portion V naught will come, and in the negative, the bottom portion of the winding, the other part of the V naught will come. So let us assume V naught is having this polarity where positive on the top and negative on the bottom. Due to the center tap, with respect to this ground, this half winding voltage will be V naught by 2. And when this V naught by 2 is the half winding voltage, this diode will be forward biased with respect to ground, and this diode will start conducting. However, this diode in the bottom will be at a the anode to cathode voltage of this diode will be negative with respect to this ground. That's why this won't be conducting. So the voltage across R will be V naught by 2 in terms of the sinusoidal nature. However, in negative cycle, similarly this bottom diode will conduct. So if we have to summarize both the pictures, in the first picture there is no center tap and any diode uh, connection. So whatever voltage will come here will come across R, and as RMS voltage is asked, anyway we are going to square it later. So I'm just showing the rectified voltage. However, the voltage will be sinusoidal only across this R, due to the RMS nature that is asked in the question. That's why I'm just showing the positive reflection of that in the negative cycle. So like I said in the previous slide, so V naught by 2 will be reflected across R. That's why in this B figure, same voltage will come with a V naught by 2 factor. And in the first figure, to calculate the RMS voltage, complete V naught sine omega t will be there. Just don't get it wrong. This is not a rectification. It's just to show that in RMS current, we are going to uh, reflect everything on the positive axis only. So, so when two voltages are in the ratio of 1:2, the RMS values comparison will also be in a ratio of 1:2. So, so when they are asked figure A to that of figure B, so as we know, when figure A has a voltage twice to that of in the figure B, so the ratio will be option 2:1, which is option B. So I hope there won't be any doubts in this question, which I'll ask. So any doubts? It was a fairly simple question.
No, sir.
Okay, yeah. So let us look at this next question. GATE 2021 instrumentation technical question 46. So consider a system with transfer function g of s, which is equal to 2 upon s plus 1. A unit step function u of t is applied to the system, which results in an output y of t. If e of t, which is output y of t minus u of t, then the steady state value of the error, which is limit t tending to infinity, is where e of t is just what is the output of the system to the input of the system, the difference, which is the error. So basically in any control system, we want the output to follow the input. Input is what we want at the output, so it should follow the input. That is what is our expectation from a normal control system. So, and how the system behave is governed by the transfer function of that system, which is given here g of s. So let us look at the question. So we can either solve this question in a time domain or in Laplace domain. We'll see both the approaches. So the first, just some useful information. Laplace transform of causal signals. What are causal signals? Which signals which do not have any past past data correlated to them, or more specifically, which do not exist before time equal to 0. So if I have to say the step input u of t, then that falls under a causal signal. So usually in the definition of Laplace transform, here minus infinity is there, but as our signal is u of t, we'll just take it from 0 only, 0 to infinity, and this is the definition of Laplace transform. It is also known as unilateral Laplace transform, but although that technical definition is not necessary here. And from that, the final value theorem states that in time domain, if limit t tending to infinity x of t is to be estimated, then in similarly S domain, limit s tending to 0 s x of s needs to be estimated. So this is the correlation between time domain and the Laplace domain. So let us look at using approach 1. So Laplace domain approach. So this error was given as e of t is equal to y of t minus u of t, output minus reference input. Just by shifting them to Laplace domain, e of s is equal to y of s minus u of s. And as we know, in Laplace domain, the system and the input gets multiplied. So y of s output response in S domain is g of s into u of s. So assuming it is an open loop system, as it is not mentioned here, whether it is closed loop or open loop, I will assume it is open loop. So limit t tending to infinity e of t is same as limit s tending to 0 s of e of s, which I showed in useful data. Now e of s, as I wrote here, y of s minus u of s, and y of s is g of s into u of s. So taking u of s as common from this second and third equation, we are left with s into g of s minus 1 into u of s. Now by substituting all the values given in the question, g of s is 2 upon s plus 1 minus 1, s is multiplied by the definition of final value theorem, and u of s is Laplace transform is 1 by s. Okay, so when we solve all this, so the final value of the error amounts to be 1 by simplifying everything. So this is the Laplace domain approach. Let us look at a time domain approach to this question. Same, e of t is equal to y of t minus e of t, e of s is equal to y of s minus u of s, and y of s is equal to g of s into u of s. This three will be the common data for both the approaches. So let us directly calculate y of s from here. So y of s is u of s into g of s. So u of s is 1 by s, g of s is 2 upon s plus 1. Let us split them into partial fractions. This will amount to 2 upon s minus 2 upon s plus 1. Then when we take inverse Laplace transform of this, so y of t amounts to be 2 into 1 minus e raised to minus t into u of t. I have forgotten to write here. Okay. Then when we put t equal to infinity, t tending to infinity in this y of t, we are left with the final value of the output as 2. And as we know, final value of u of t is always 1 because it is constantly 1. So the error between output and the input is limit at t tending to infinity, both y of t minus e of t is equal to 1. So by both approaches, we are getting answer as 1. So you can proceed with either of the approach. So answer to this question is 1. Okay. However, nothing is mentioned about open loop or closed loop, so you can go with open loop for now. Uh, but if it was explicitly mentioned as closed loop, so instead of this g of s here, you should have taken g upon 1 plus g. However, both the approaches remain the same, uh, and you can apply the same principles and solve the question for any other variation of this question. So any doubts in this question?
No, sir.
Okay, fine. So next question, GATE 2019, instrumentation technical question 9. If each of the value of inductance, capacitance and resistance of the series LCR circuit are doubled, the quality factor of the circuit would be, it's written as Q factor, which the full form is quality factor. So what will happen is, will it reduce by a factor of root 2, reduce by a factor of 2, increase by a factor of root 2, or increase by a factor of 2? So let us understand what this quality factor is in the circuit. So before we solve this question, so this is a series RLC circuit. So let us look at which is excited by a AC source. So as we know, when AC source is involved, AC currents will flow and the impedances will be seen will be proportional to the frequency of the source. So XL, which is the inductive reactance of the circuit, which is 2 pi FL, is omega L, and inductive capacitive reactance will be XC, which is 1 by omega C. So it is obvious that when XL is greater than XC, the circuit is inductive, and XC is greater than XL, the circuit is capacitive. Total reactance of the circuit will be, from basic power systems or networks theory, XT is equal to XL minus XC. This is the normal convention which we follow. Usually on the left hand side, or XC minus XL, whichever you are comfortable for this question, but XL minus XC is the usual convention. So the total circuit impedance will be Z, which is equal to under root R square plus X total square, which is the quadratic sum, is equal to R plus JX, where J represents impedance is at quadrature with the resistance. So as we mentioned here, X total circuit reactance will be XL minus XC. So when will XT be equal to 0? If we have to just ask a question to ourselves. Uh, so that is when XL is equal to XC, because by definition XT is equal to XL minus XC. So for XT to be 0, XL should be equal to XC. When will that happen? We'll equate both the values and we'll find the value of F. So by shifting terms here and there, we'll get F square is equal to 1 upon 4 pi square LC, where F will be 1 upon 2 pi root LC, or converting hertz to radians per second, omega R will be 1 upon root LC. Omega R represents the resonant frequency, or resonant in radians per second, that at which XL will be equal to XC. So this impedance or the reactance of this total network will be nullified, and only resistance will remain in the circuit. So what I explained earlier, I'll just explain it in a diagrammatic form, where the total Z was this R square plus XT square, and when XL is equal to XC, XT goes to 0, so only R remains in the Z. That is shown in this figure, where at resonant frequency Z is equal to R, which is the total impedance, and at lower frequency it is highly capacitive, because in capacitance 1 upon omega C, when omega is very low, XC goes to infinite. When omega is equal to 0, that's why. And when omega is towards infinity, XL becomes very high. So either ends, it is highly capacitive towards the left or highly inductive towards the right. Only at resonant frequency, which is 1 upon root LC, the impedance is R. Impedance seen by the circuit to a AC source is R. Now when resonant frequency occurs, the impedance is R, which is at the lowest. That will mean that the current seen is the maximum, because when impedance is lowest, current will be V upon the impedance, and more specifically at resonant frequency it will be V upon R, because that is the impedance seen by the circuit. So current will be maximum at resonant frequency. So this peak in the current which is there, this governs what is the nature of the response, and this magnitude depends on the value of the resistor. So uh, just looking at the figure on the right hand side, whether R is small or whether R is high, that peak will be suppressed or more peaky in the nature, and the pattern will be same. XC greater than XL will be on the left, XL greater than XC will be on the right. When we look at the bandwidth by traditional control system theory, where we take it at 0.707 or whatever the Imax value is, peak value of the current, we take it at 1 by root 2 times of that max value, or minus 3 dB decade. That is the bandwidth of the system. I am not going into the mathematics, but I am just explaining you the concept. So this Q factor is defined as the bandwidth is equal, the relation is bandwidth is equal to resonant frequency upon the Q factor. I would suggest you do the derivation. I'm not going to show the derivation because that is very lengthy derivation here. But if you want, I can take it in the next class. But for now, just understand the concept of how it is happening in the circuit, visualize. And when you derive, the quality factor determines what is the peaky nature of this waveform. Basically, it determines how much peak is happening in the system. So it comes out to be Q is equal to 1 by R under root LC for this series resonant circuit. So in the question it was asked if values of inductance, capacitance and the resistance are doubled, the Q factor will be of the circuit will be what? So if everything is doubled, L and C, if both are doubled, they will nullify each other in this under root because of division. However, R will be doubled, so quality factor will be reduced by half. So it will be reduced by a factor of 2, which is option B, answer to this question. The derivation is quite long, you can take it up. However, the derivation people are not going to ask you, so I'll suggest you do it once for series RLC and parallel RLC and see what are the Q factors for both the circuits. I'm not going to tell you the direct answer to that. You do it once, and once is enough, and then you will understand what this Q factor is, and pretty much it's a interesting topic for the GATE question paper setters. Frequently this question has come in the series RLC circuit, so just look into it. But I hope whatever I taught in this question is clear to you guys. Any doubts?
No, sir, clear.
Okay, fine. So that's it for today. I plan to take these 3 questions only. So if any other doubts are not there, we'll conclude the session. It's fine.
Yes, sir. Thank you, sir.
Thank you.